So let's dive right in. Well, writing machine learning pipelines is hard. And orchestrating, serializing, parallelizing, and also deploying to production those pipelines is even harder. It can be frustrating when you're hitting walls for those things that at first seems simple, like parallelizing, saving to disk, loading, and everything. So if you use the good design patterns, you can make things simple and also easier, maybe not easy, but at least easier. So there are several problems that must be addressed, and I think it's really important to bridge the gap between machine learning and clean code. So that's the subject today. So my name is Guillaume Chevalier. You can add me on LinkedIn, Facebook, Twitter, and all the other social media. And I'm the founder at Neuraxio. So let's see a code refactoring tutorial in which you'll be able to look at some code, see how you can restructure it better, and you'll be able to think on your own, technically speaking, how you could apply the same principles to your own code. So here is the code. So you're probably quite used to write some code like this. So you take the mean of your data, you take the standard deviation, you normalize with your data by subtracting the mean, dividing by the standard deviation. So now you have normalized data, and you loop on it. So you fit your model to your data, and you shuffle your data before fitting it. And then you do some predictions on your test data that you also need to normalize the same way that you've learned at the beginning. So this is the way that is simple yet dirty to do. You might want to use instead a normalizer. So you declare a normalizer like that here, and then you fit your normalizer to your training data and you transform it. So like that, you can then proceed to do the rest of what you were doing, and you can use the normalizer here instead of doing the math like manually. So by properly pushing your technical code into objects like that, you get to write clean code. So the normalizer does only one thing, and here at the high level place in your code, you can manage simpler things. It's more lightweight as well for your mind to take these variables into consideration to play with them. So here's how you could code your normalizer. So we inherit from a base step, which is from our own framework here. And what is a base step? Then it's only a simple data fitting and transforming step within a machine learning pipeline. So this is very, very, very similar to the base transformer of scikit-learn. So when you inherit from that, you can be compatible with all the rest of the functionalities that we'll see below, or most of them. And what you need to do is to define a fit method where here some state is learned for the mean and standard deviation on your data, and how to transform your data as well. So like that, you can then proceed structuring your code into the pipe and filter design pattern, which is really, really, really good in machine learning. So you might recognize here this structure, which is inspired from scikit-learn, the pipeline here. There's the same object in scikit-learn, and we've built it anew with a very, very similar API. You can also put some scikit-learn objects directly into that here, and it will work. So we have our normalizer, or model that we were fitting, and also the data shuffler has been extracted to an object here that we can import. So this makes the code even more simpler, and here you can proceed to fitting your pipeline on your data. So you'll realize that here we're training for 10 epochs on our data set. So every step here will fit again and again on the data 10 times. So when we'll come to mini batching later on, you'll realize that it would be better for your normalizer to be able to adapt to new training examples, but still keep some of its old state and slowly but surely update its internal state when it sees new data to normalize in an even better way over time, just like batch norm, but not like batch norm at the same time. So you can proceed to predict on your data, and predict is different from transform. Transform that we've seen above when we were transforming data. The simple difference is that when you call predict in scikit-learn as well, it's the same API. You're kind of in test mode. So all this is great and fun, but you might need to do some things differently in test mode and train mode. So we'll see that later. You can add some features. So let's say you need to pre-process your data before normalizing. So you could have a column chooser here, which can process multi-dimensional arrays of the dimension you'd like. But here suppose it's 2-dimensional. So you could apply a date encoder to the first 2 columns, and on the 3rd column, you could use a categorical enum to encode your data, just like a one-hot encoder, which is commonly used to transform integers into many numbers that are all with values of 0 and 1 with the value of 1 at the good index where the integer was pointing to. So here we would have 5 categories. So here, for instance, the date encoder could take the year, month, week of month, and day of week, and day of year, things like that, and encode them into some circles with sinus and cosinuses. So you could create more feature than there was as inputs with this column chooser to apply transformation. Same for your categorical enum here. You would take the 3rd column and you'd get 5 numbers at the output, and the features will be concatenated together before going through the rest. So there is another very cool design pattern that we've come up with in two kind of pipelines, and it's the wrapper. It's also named the decorator design pattern. So basically, it's an object that eats another one. It surrounds another object to modify a little bit its behavior or add conditions to its execution, things like that. And it is still doing the work of the other object underneath. So here, as I've discussed, you might want some different behavior during fitting, transforming, and predicting, so between train and test when you play with your data. So you would surround your data shuffler with a train-only wrapper here, because you only want to shuffle your data at train time and not in production mode later on when you're predicting. So this is really cool, the wrapper. It's useful. There are some kind of other wrappers that are really interesting, in which you can do for loops. So let's say you receive a 3-dimensional array here, and you'd like to apply a step that is used to processing 2-dimensional data here. You could use the for each data input wrapper, and it would automatically loop on your external dimension of your data. Or you could have a transpose step before if you want to trade some dimensions and things like that. It's really cool. So you can use NumPy arrays, lists, different data types between your steps, some strings if you wish as well. It's really made to be flexible and to be able to work with any kind of data and with any library. For instance, you could use TensorFlow for the model. So here you will see that you can do mini batching and parallel processing. Well, if you add this mini batch sequential pipeline wrapper, which is also a pipeline because it accepts a list of steps, just as the pipeline does. So here, this one, it takes the data it has at the input, it splits it into some mini batches of the specified size, and then it will repeatedly fit the model onto those batches, or transform as well if you're in transform mode, or fit transform if you're in fit transform mode, chaining one after the other for sure. So also note that it's possible that your batch size, when processing the last few data examples, doesn't pile up to this even number right here. So you could have more parameters and options here to either drop this incomplete batch during training or keep it and do other things. Another really important design patterns that we've used in a lot of our projects is the repository. So this is a really, really classical design pattern. Basically, a repository is an object, more especially an abstract class, that offers an interface, so methods, an API, to just load and save data, right? So the goal of this is that when you're in development mode or when you're in production mode, and you can just swap the repository implementation that inherits from the same abstract class and have this abstraction available to process your data. So whatever you send to your pipeline, you'll be able to load it, whether it's on disks or some kind of things in your RAM, or if it's in a MySQL database or NoSQL database or something like that. So basically here, some of you might have already used the service locator design pattern or a context object. The common thing with a context and a service locator is that both of them contains services. So here we have a context and we add the repository we want, which is here, or training data repository, and we set it into the pipeline. So you could program here a pipeline step that accepts some IDs, only integers of training and examples, and then convert them to loaded training examples. So you could add some assertion in this pipeline that when you're in this step, you can have access to the whole pipeline's context here. So you can assert that the base repository is in the context, and you can roll on with that. So what's really cool with this is that, let's say you have a really, really, really huge data set, then it's possible to only load the IDs, or even IDs of IDs if you want more things complicated. You can do anything you want. It's super flexible. So you can have some IDs and then some mini batches, and only when you're ready, you could load your images, converting those IDs to loaded data by calling your repository once you're in this step here. So this is also very interesting in cases where you want to do some oversampling or undersampling, such as when you have imbalanced classes in your dataset. Let's say you're doing cancer prediction and only 1% of the time you have a positive case, then you want to sample more often the positive cases. So you would send in more IDs of the positive cases, and you would load them whenever needed here within the batch. Or let's say you work with satellite image data, then you could just simply randomly take crops of your images from your database. When you're in train mode and when you're in test mode, you just load some very specific IDs, and you can have a train-only wrapper on something and a test-only wrapper on the step below to alternate the way it works. There are also more features like that that we won't discuss now, but the goal is to be fully flexible and to be able to work with the GPU as well and with databases in big data context and to be able to put things in production. So here we've moved the data shuffler at the beginning and we used a sequential queued pipeline. This one is a bit different than the mini batch sequential pipeline, in which the sequential queued pipeline will put every 4 of those steps it contains into a different thread, and it will add a queue between each step. So if one step processes the data faster than the next step, then it will output data to the queue between the two steps, and the queue will be consumed by the next step. So here, just by using one class, you can parallelize everything that's within what that is wrapped inside this class. And you can specify the number of workers, a max queue size, and also a batch size to use mini batches to fill your queues. Here note that we have a number of workers per step. So as well as having all of those steps in parallel, let's say this one could have 4 threads as specified here. So during the fit, it wouldn't work like that. So you could fit your model only onto one thread, for instance. But once you have a transform call, you could have more threads to transform in parallel to dump things into your queue, things like that. So it's really interesting. And if you have TensorFlow in your model, you might object and say, oh, it will fail to be parallelized by this object right here, the pipeline, because your TensorFlow model uses an external library, which is TensorFlow, and thus is not natively serializable in Python and would require the TensorFlow saving mechanisms. Well, we'll see that later. You can build your own serializers, savers, and it will work properly to parallelize all of your steps and save them to disks and reload them later on to put things in production after you've trained and save your pipeline. So training your pipeline. Know that for your model, you can set some hyperparameters. So let's say you set here 12 neurons in your hidden dimension in your neural network. You could also set to this model a hyperparameter space. So here you could say this number of neurons will switch between 6 and 750 neurons. So you can automatically tune that later with automated machine learning. So automated machine learning is just a for loop, basically, with some intelligent sampling of the next hyperparameters to try in the space to try to get the best model according to a selection strategy, which could be specified in here. And yeah, it's automatic hyperparameter tuning for your model. So you can specify a way to split your data across your trials. You can try 100 times to solve this problem differently, and you use a specific score. Here we have a function that is the accuracy, and we want to reach a higher score instead of lowering the score. So you can save your results somewhere in a repository. So here it's a JSON repository, which writes the results on disks. We provided this repository for everyone to use by default. There's also a in-memory repository if you want to keep results only in your RAM and not on disks. And you could as well create your own repository, let's say, to save things to a database or some kind of shared cloud resources to load and execute many automatic machine learning loops on different computers with the same shared repository for the trials to have the hyperparameter selection strategy use this every time in parallel. So you can fit your automated machine learning loop here. You can fit it and then get the best model, and that's it. Voila. So about serializing your pipelines. So your model uses TensorFlow. You want to create a model saver that will take the TensorFlow out of this model object, serialize it to disk using the TensorFlow serializers, and delete this TensorFlow part of things inside your object here so that your object be kind of naked or empty or stripped of its TensorFlow parts. And this way, you'll be able to, upon calling the save function of the whole big pipeline, the save function will specify a folder, and your saver will be able to use this specified folder and subfolders with the name of the model at a very specific place to save things, and you can serialize everything like that. Same thing for loading the pipeline, and the parallelization, as I've discussed above, in the threaded queues and everything, can use the savers as well to serialize your pipeline to another thread to parallelize it whenever needed. So all this is really cozy. It's fun. It's simple to play with. It's really comfy, and all this in the goal to reduce pain and frustration during coding, to be finally able to do what you wanted to do while you were stuck. Because with the scikit-learn pipeline, you couldn't do that. If you save it with joblib or pickle, for instance, it would just say that your model is not serializable, and you would start to rage, basically, or things like that. And all the functionalities here, it's really, really needed for putting pipelines to production. So to conclude, we've built here a simple machine learning pipeline example, and it's automatically tuned and take the best models. We also have ways of visualizing the different trials and different hyperparameters and scores and losses over times with the epochs for every and each of the 100 trials and everything. So you can get your best model, save it, and then serve it. So that's it. Deploy to production. Yeah. So this is Neuraxio. You can visit the documentation website. It's free to use under the Apache 2 license. It's also the backbone of our products here at Neuraxio. So we're offering services and products for companies, especially in the space of time series processing, such as financial transaction histories, to do predictions. When will people buy? What will they buy according to a catalog of products and things like that. We also do some natural language processing and things like that. So we have approximately 10 clients right now. We're a team of 5, and don't hesitate to follow us on social media. So thank you for listening.
Awesome, man. Thank you so much. Our first question is, do you support Bayesian optimization in the automatic hyperparameter tuning? Bayesian optimization? I don't think I pronounced that
Bayesian, right. Yeah, I think it's we need to see, actually. Please open an issue for that. So right now we have 2 automated machine learning hyperparameter selection strategies. So the first one is obviously the random search, classic, and the other one is the Parson tree estimator, also named HyperOpt or TPE. So we've coded it again, as the HyperOpt library was kind of lagging behind in terms of design patterns, clean code, usability, and things like that. So we've coded this again. So what it does is that it looks at the previous hyperparameters tried, the scores that were obtained, and what has not been tried yet, as well as what was performing well, and it's trying to take guesses for the next best thing to try in this space. So it works with Gaussians and things like that. And we've also thought about doing selection strategies like that could be tuned themselves to be able to find the best hyperparameters even faster with like meta automated machine learning, things like that. And we could have done it, but it wasn't really practical for solving our project. So this library was developed first for our consulting work and then for building our own products. So it was facing industry needs and issues and less of research needs and issues. So that's how it took place. So hopefully it's really useful.
Awesome. Thank you for that. And we have another question from Jerome. He said, you mentioned in the beginning of your presentation that using simple data structure is simple yet dirty. Can you further explain why it's important to avoid using this kind of dirty solution and why you would rather use abstractions as pipeline steps?
Good. Okay. So one thing is that the brain can only take into account 5 to 7, sometimes a little bit more, but it's rare, variables at the same time. So here you already have a load of variables in the same code space. And not only that, you already see that there is a duplication of code, which is a really bad sign. Here you subtract, you divide, and you see, as I was highlighting, that you see the same pattern below. It's subtracting and dividing. In fact, I could have wrote this like this and like this and STD, and it would be just the same thing. It could have been written in one line like that. It's the same thing. So you could extract this to a function or something, and it would already make things simpler. So when you change something, you also change it at the other place automatically. And while it's extracting things like that, then you want to put things that belong together. So when you're building a normalizer like that, you have just this behavior here next to the other behavior. Moreover, let's say that you're a kind of manager here, someone a bit bossy who doesn't want to get into the deep stuff of its employees. So here you would have a normalizer, and you will tell your normalizer to be autonomous and do its job, basically, without doing its job by yourself, without micromanaging. So there are some metaphors and parallels that can be pictured like that here. So this is another reason to do that, because when you start leaking the logic out of your object, you already see the symptom here. You duplicated code. And once you start duplicating code, you duplicate it everywhere. And when you do that, it's really hard to change things. And when you tell objects to do what you need to do, you just add methods in the object, and you will be able to reuse that whenever needed. And there are lots of other reasons why it's needed to have proper separation of abstraction levels. You want to keep your mind clean. And here's just an example. There's one normalizer, one model. Don't even try to imagine the whole stuff here with everything here. It would be one big file of 1,000 lines or 2,000 or even worse. And you would click on a variable, you would be trying to go see elsewhere what it's doing, and you would get a headache. So you would be very, very frustrated from that. And it also takes more time to maintain and to modify. So here, you've also gained a normalizer object that you can reuse in your future project. So not only your code is more modular and more simpler, but it's more reusable in your other projects. So you can end up coding lots of classes like that. And when starting a new project, just putting them together into, bam, a pipeline like that. Personally, we've achieved some good speed of development like that because we've done many things for several different projects. I've personally participated in more than 57 AI projects or collaborated in them. So with time, it's getting faster to reuse things like that as well. But it's still worth to do that for even a one-off project, I think. If you want to deploy to production, if you're just trying to get a high score for a research paper, then obviously you might want to skip this clean code thing. But whenever you want something that will live in time and that will need to be maintained and that runs into production and needs to work for sure, you want to do that. Also, there's another plus to wrapping your objects into some classes like that. You can unit test this class. You can write a test and create a normalizer, send data to it, and then assert and ensure that the answer you get is what you've expected. So you can write test suites like that when you have separated behavior instead of one big mess. So you want to be able to test your code to ensure that it won't crash in production as well.